Welcome to the History of Simple Things, where we delve into the fascinating history behind the little things that shape our world. Have you ever wondered how something as heavy as a commercial airplane stays up in the air, traveling faster than the speed of sound? It's all thanks to the marvel of engineering we call jet engines. They are one of the most powerful machines ever created, allowing us to cover vast distances in just hours. But how do these incredible machines actually work? Let's break it down in simple terms. A jet engine at its core works on a very basic principle. Suck in air, compress it, add fuel, ignite it, and shoot it out the back. This process creates thrust, which pushes the airplane forward. It's very similar to how a balloon works. Think of it like this. When you blow up a balloon and let go, the air rushing out propels the balloon forward. Jet engines take this concept to the next level with precise engineering and high temperatures. Now imagine that simple balloon idea on a much grander, more powerful scale. We're talking about air being sucked in at over 900 kilometers per hour and temperatures inside the engine that can reach up to 2,000 degrees Celsius. That's the magic happening inside the engine every time you see a plane take off. But to understand how it all works, we need to break down the jet engine into its main components. The fan. The first thing you'll see when you look at a jet engine is that massive fan at the front. The fan's job is to take a huge amount of air and push it into the engine. Roughly 80% of this air bypasses the engine's core, going around the outside, and this actually helps to create thrust more efficiently. It's kind of like a turbocharged wind tunnel. The faster the air moves through the fan, the more thrust the engine can produce. And the bigger the fan, the more air it can suck in, which is why newer jet engines tend to have larger fans. The compressor. After the fan, the air is funneled into the compressor. This part of the engine works exactly like it sounds. It compresses the air. You can think of it like squeezing a balloon. The air inside gets denser and more pressurized. The compressor is made up of multiple spinning blades that work in stages, each one compressing the air even further. By the time the air reaches the end of the compressor, it's 20 to 30 times denser than when it first entered. This dense air is crucial because it allows the engine to produce a powerful explosion later on. Next, the air enters the combustion chamber, where things really start to heat up, literally. This is where fuel is added to the compressed air. The fuel used in jet engines is usually a special type of kerosene because it has a high energy content and burns efficiently. When the fuel mixes with the compressed air, it gets ignited by a series of small spark plugs inside the combustion chamber. This causes an intense explosion, heating the air to incredibly high temperatures. Remember that 2,000 degrees Celsius we talked about earlier? That's happening right here. The turbine. Now all that hot, high-pressure air has to go somewhere, and this is where the turbine comes in. As the superheated air rushes out of the combustion chamber, it spins a series of turbine blades, which are connected to the compressor at the front of the engine. So the turbine is actually what powers the compressor, creating a loop where the engine keeps running as long as fuel is added. These turbines are incredibly strong, built to withstand extreme temperatures and pressures, yet they need to be lightweight to keep the engine efficient. The exhaust. Finally, after spinning the turbines, the remaining hot air shoots out of the back of the engine through the exhaust nozzle. And this is where the real magic happens. As the hot air escapes, it propels the aircraft forward. The faster the air leaves the engine, the more thrust is generated. This final blast of air is what pushes the plane through the sky at hundreds of kilometers per hour. The engine has essentially converted fuel and air into a powerful force of motion. Thrust is the force that moves the plane forward, and it all comes down to Newton's third law of motion. For every action, there is an equal and opposite reaction. In the case of a jet engine, The action is the hot air being expelled out the back, and the reaction is the plane being pushed forward. Think about it like jumping off a skateboard. When you push your legs backward, the skateboard moves forward. The jet engine works the same way, but on a much larger scale and with air instead of legs. Not all jet engines are created equal. There are several types, each suited for different kinds of flight. Turbojet engines. These are the most basic type of jet engine, where all the air goes through the core, compressor, combustion, and turbine stages. They were the first kind of jet engines and are still used in some military aircraft today because of their high-speed capability. Turbofan engines. This is what you'll find on most commercial planes. The large fan at the front creates most of the thrust, making these engines more fuel-efficient and quieter than turbojets. A smaller amount of air actually goes through the engine core, while most bypasses around it. Turboprop engines. These are jet engines that use a propeller instead of a fan. They're more efficient at lower speeds and are often used on smaller planes or for regional flights. Ramjet and scramjet engines. These are special types of engines used for supersonic and hypersonic flights. They don't have moving parts like compressors and turbines. Instead, they rely on the aircraft moving at incredibly high speeds to compress the air naturally before combustion. These engines are mostly used in military or experimental aircraft. Jet engines have come a long way in terms of efficiency. Modern engines are designed to burn less fuel while producing more thrust, making flying cheaper and greener. Engineers are also working on new technologies, like hybrid engines, that can reduce emissions and noise pollution even further. But despite their efficiency, jet engines do have an environmental impact. They release CO2 and other greenhouse gases into the atmosphere, which contributes to climate change. This is why there's a growing interest in alternative fuels like biofuels and electric planes that could one day replace traditional jet engines. So the next time you're sitting on a plane, gazing out the window as the engine roars to life, you'll have a deeper appreciation for the sheer ingenuity packed into that machine. What you're witnessing is the result of decades of engineering advancements, human perseverance, and an understanding of complex physics that have made flight not just possible, but routine. Jet engines are a perfect blend of simplicity and sophistication. They take a simple idea, moving air and fuel through a chamber and igniting it, and turn it into a system that can send a massive metal tube soaring at speeds faster than sound. The next time you take off on a jet-powered flight, you're not just traveling from one place to another. You're part of a legacy of human innovation and a glimpse into the exciting future of aviation. As we continue to push the boundaries of what's possible, it's worth remembering how far we've come and how much farther we'll go. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Airplanes are marvels of modern engineering, designed with precision and purpose to ensure safety, efficiency, and reliability. One of the lesser-known but critically important features of aircraft are the needle-like protrusions that can often be seen on the wings, tail, and fuselage. These small, seemingly insignificant appendages are actually crucial components known as static dischargers, also referred to as static wicks. Their primary function is to safely discharge static electricity that builds up on the airplane's surface during flight, preventing potentially dangerous situations. But to fully appreciate the role of these static dischargers, it's important to understand the nature of static electricity, how it accumulates on aircraft, and the potential consequences if it's not properly managed. Static electricity is a common phenomenon that most people experience in their daily lives, often in the form of small shocks when touching a metal object, after walking across a carpeted floor. It occurs due to the buildup of electric charge on the surface of objects caused by friction between materials. In the context of aviation, static electricity is generated when an airplane flies through the atmosphere, particularly in conditions where there is a high degree of friction between the aircraft's surface and the surrounding air molecules. As the airplane moves through the air at high speeds, it rubs against particles in the atmosphere, such as dust, moisture, and even ice crystals. This interaction creates an electrical charge on the airplane's surface, and if left unchecked, this charge can build up to significant levels. The buildup of static electricity on an airplane can pose several risks. One of the primary concerns is its impact on the aircraft's communication and navigation systems. Modern airplanes rely heavily on electronic systems for communication with air traffic control, navigation, and other critical functions. Static electricity, if not properly managed, can interfere with these systems by generating electromagnetic interference, EMI. This interference can cause disruptions in radio communications, leading to garbled or lost messages between the pilot and air traffic controllers. In extreme cases, it can even affect the performance of the aircraft's navigational instruments, leading to potential deviations from the intended flight path. Another significant risk associated with static electricity is the possibility of sparks. When the static charge on an airplane reaches a certain threshold, it can discharge in the form of a spark. This is particularly dangerous in situations where the aircraft is refueling, as a spark near the fuel tanks or fuel lines could ignite the fuel vapor, leading to catastrophic consequences. To mitigate these risks, airplanes are equipped with static dischargers, the needle-like protrusions that are carefully positioned across various parts of the aircraft's surface. Static dischargers work by providing a controlled path for the excess static electricity to dissipate safely into the atmosphere. These devices are typically made of conductive materials such as metal or carbon and are designed to be lightweight and durable. The pointed shape of the static dischargers is crucial to their function, as it allows for the efficient discharge of static electricity. According to the principles of electrostatics, electric charges tend to accumulate at sharp points or edges. The needle-like shape of the static dischargers takes advantage of this principle, allowing the accumulated static charge to be released gradually and harmlessly into the surrounding air. The placement of static dischargers on an airplane is strategic and deliberate. They're usually installed on the trailing edges of the wings, tail, and other extremities of the aircraft. These locations are chosen because they are the points where static electricity is most likely to accumulate due to the airflow over the airplane's surface. By positioning the static dischargers in these areas, engineers ensure that any buildup of static electricity is efficiently discharged before it can cause problems. The number and distribution of static dischargers on an aircraft can vary depending on the size and design of the plane, as well as the materials used in its construction. In addition to preventing interference with communication and navigation systems, static dischargers also play a role in protecting the aircraft's structural integrity. During flight, particularly in stormy or turbulent conditions, an airplane can encounter various forms of electrical phenomena, such as lightning strikes and St. Elmo's fire. Lightning strikes, while relatively rare, are a significant concern for aircraft. When lightning strikes an airplane, it typically travels along the metal skin of the aircraft and exits through a static discharger, minimizing the damage to the plane's structure and preventing electrical surges that could harm onboard systems. St. Elmo's fire, on the other hand, is a phenomenon where a visible blue or violet glow appears around the aircraft, particularly around sharp points like the static dischargers, as a result of the ionization of the air due to the aircraft's electrical charge. While St. Elmo's fire is not dangerous, It is a visible indication of the electrical activity around the aircraft and the effectiveness of the static dischargers in managing the static charge. The effectiveness of static dischargers is not only essential for safety, but also for the overall performance of the aircraft. As aircraft continue to evolve with advanced materials and designs, the management of static electricity becomes even more critical. For example, many modern airplanes incorporate composite materials, such as carbon fiber, which are lighter and more fuel-efficient than traditional aluminum. However, these materials are less conductive than metal, making it more challenging to manage static electricity. As a result, engineers must carefully design and place static dischargers to ensure they provide adequate protection, even on composite surfaces. While static dischargers are a critical safety feature on modern aircraft, their presence is often unnoticed by passengers and even some aviation enthusiasts. These small needle-like protrusions are a testament to the meticulous attention to detail that goes into the design and operation of airplanes. They represent a simple yet elegant solution to a complex problem, allowing airplanes to safely navigate through the skies without the threat of static electricity interfering with their systems or compromising their structural integrity. To conclude, the needle-like protrusions on airplanes, known as static dischargers, are essential components that play a vital role in maintaining the safety and performance of the aircraft. By providing a controlled path for the discharge of static electricity, they prevent interference with communication and navigation systems, reduce the risk of sparks during refueling, and protect the aircraft from the effects of lightning strikes and other electrical phenomena. The design and placement of static dischargers are carefully engineered to ensure they function effectively, even on modern aircraft made from advanced composite materials. Although often overlooked, these small devices are a critical part of what makes air travel safe and reliable, highlighting the importance of every detail in the complex world of aviation. Airplane windows are rounded instead of square, due to critical safety concerns and lessons learned from early aviation tragedies. The design of aircraft involves meticulous engineering, where every detail matters in ensuring the safety and efficiency of the aircraft. One key detail that might seem trivial is the shape of the windows. However, the transition from square to rounded windows is deeply rooted in the history of aviation and directly tied to some of the most tragic events in early commercial jet travel. Understanding this shift requires delving into the physics of pressurized cabins, material stress distribution, and the role of engineering design in preventing catastrophic failure. In the early 1950s, the de Havilland Comet, the world's first commercial jetliner, revolutionized air travel. It was faster, could fly higher, and brought with it the modern experience of commercial flight. However, this revolutionary jet also introduced a fatal flaw that tragically took lives. Within a year of its introduction, 3 Comet aircraft disintegrated in mid-air, causing the loss of hundreds of lives. These catastrophic failures puzzled engineers and experts until a thorough investigation revealed a critical design flaw: the aircraft's square windows. At high altitudes, aircraft cabins are pressurized to keep passengers comfortable and alive. The pressurization of a cabin results in a significant difference between the internal and external pressures, which puts stress on the airplane structure, including the windows. In square windows, the sharp corners become points of concentrated stress. In technical terms, these corners act as stress concentrators, where forces accumulate and weaken the material over time. Under repeated pressurization cycles, as the plane ascends and descends, these corners would develop tiny cracks that would eventually propagate and lead to structural failure. The investigation into the Comet crashes revealed that the square window design had led to these catastrophic failures. The sharp corners could not evenly distribute the stress, making them susceptible to cracking under repeated stress cycles. The lesson was a harsh one, but clear. For the integrity of the aircraft's structure, the windows needed to be redesigned. Engineers quickly realized that the solution lay in eliminating the sharp corners by adopting rounded windows. Rounded or oval windows, by their nature, distribute pressure more evenly around their edges, preventing any one spot from becoming overly stressed. The continuous curve of a rounded window allows for the forces acting upon it to be dispersed more gradually, reducing the likelihood of a catastrophic crack forming. This seemingly simple design change played a crucial role in making air travel as safe as it is today. Moreover, the importance of rounded windows extends beyond preventing structural failure. The design also has implications for passenger comfort and the overall flight experience. In addition to handling the stresses of pressurization, rounded windows offer passengers a more comfortable view. Square windows with their sharp lines and right angles tend to distort the view more than rounded ones, especially near the edges. Rounded windows, by contrast, provide a more uniform and aesthetically pleasing visual experience. Additionally, the rounded edges reduce the likelihood of glare and reflections that might be distracting or uncomfortable to passengers. From an engineering perspective, the transition to rounded windows also underscores the importance of redundancy and fail-safes in aviation design. Aircraft are subject to extreme conditions, from rapid changes in pressure to variations in temperature and turbulence. Every component, no matter how minor it seems, is designed with the intention of minimizing risk. In the case of aircraft windows, the lessons learned from the Comet disaster led to rigorous testing standards and improved design protocols. The rounded window design has become an industry standard, ensuring that commercial jets can withstand the stresses of pressurization over thousands of flight cycles. Furthermore, the science behind the shape of airplane windows also ties into broader principles of structural engineering and design. The shape of an object significantly affects how it responds to forces acting upon it. Rounded shapes in general are more stable and are less likely to develop stress points where cracks could form. This principle is evident not only in airplane windows, but also in various other fields of engineering. From bridges and tunnels to architectural domes, curves and rounded shapes are frequently employed where stability under pressure is crucial. In aviation, where safety is paramount, adopting such a design is non-negotiable. In addition to their practical role, airplane windows also serve an important role in maintaining the structural integrity of the fuselage. The fuselage of an airplane is a pressurized tube, and any openings in it, such as windows or doors, represent potential weak points. By rounding the windows, engineers ensure that these weak points are as robust as possible. The smooth, curved shape aligns more naturally with the cylindrical structure of the fuselage, helping to distribute loads more evenly. This, in turn, reduces the overall stress on the aircraft's frame, allowing it to endure more flight cycles without degradation. In conclusion, the rounded shape of airplane windows is a product of both historical lessons and fundamental engineering principles. What began as a response to fatal design flaws in early jetliners has evolved into a universally accepted standard in aviation. The shift from square to rounded windows has been driven by the need to ensure passenger safety, improve structural integrity, and enhance the flight experience. The transition underscores how even small design changes can have far-reaching consequences in industries where safety is paramount. Today, rounded airplane windows stand as a testament to the progress made in aviation design, embodying the principles of stress distribution, structural integrity, and passenger comfort. As we continue to refine and advance aircraft technology, the rounded window serves as a reminder that every detail, no matter how minor it may seem, plays a vital role in ensuring that the skies remain safe for all who travel. Thank you for joining us in this journey. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Imagine you're at an airport, watching as a massive commercial airliner rolls onto the runway. It's hard not to marvel at the sheer size of it. Hundreds of tons of metal, engines, passengers, cargo, all lined up and ready to take off. As the plane gains speed, the engines roar, and just as it seems it could never defy gravity, it begins to ascend. But how does that happen? How do aircraft wings, these seemingly simple structures, generate the lift needed to carry something so enormous into the sky? In today's video, we're going to delve deep into the science of flight, breaking down the principles behind how wings generate lift and how humans have harnessed this knowledge to fly. To begin understanding lift, it's important to know that an aircraft in flight is constantly subjected to four key forces: lift, weight, or gravity, thrust, and drag. Lift is the force that acts perpendicular to the direction of airflow and counters the downward pull of gravity, effectively keeping the aircraft in the air. But lift doesn't act alone. It works in concert with thrust, which moves the aircraft forward, drag, which resists its motion, and gravity, which pulls it toward the earth. An airplane stays in the air by balancing these forces. When lift equals the weight of the aircraft, the plane remains at a steady altitude. When lift exceeds weight, the aircraft climbs. Conversely, when weight exceeds lift, the aircraft descends. Of all these forces, lift is the one that tends to capture our imagination the most. After all, how can a wing, which is essentially just a shaped piece of metal, generate a force strong enough to lift thousands of pounds into the air? The answer lies in the shape and behavior of the wing, also known as an airfoil. The design of the airfoil manipulates the flow of air around it, creating the conditions necessary for lift to occur. The cross-sectional shape of an airplane wing is referred to as an airfoil. The design of the airfoil is one of the most critical factors in the generation of lift. A typical airfoil has a curved upper surface and a flatter lower surface. This specific shape is integral to the physics of lift because it influences the way air flows over and under the wing. As the plane moves forward, air splits when it encounters the wing. Some of the air travels above the wing and some travels below it. Due to the curvature of the upper surface, the air flowing over the top has to travel a greater distance compared to the air flowing underneath the wing. According to the Bernoulli principle, faster-moving air results in a lower pressure. Since the air over the top of the wing moves faster than the air beneath it, a pressure difference is created. The air pressure beneath the wing is higher than the pressure above it, and this difference in pressure creates an upward force. This is often described as the Bernoulli effect in flight, though it is not the whole story, as we'll discuss in a moment. The pressure differential is crucial, but it's only one aspect of what generates lift. The exact shape of the airfoil varies depending on the aircraft and its purpose. For instance, gliders have highly curved wings designed to maximize lift and minimize drag, while fighter jets may have thinner wings designed for speed and maneuverability. The Bernoulli principle provides a partial explanation of lift by describing how the speed and pressure of air relate to each other. According to this principle, in a steady flow of fluid, in this case air, the increase in the fluid's speed results in a decrease in pressure. So the air moving faster over the curved upper surface of the wing has a lower pressure compared to the slower moving air below the wing, creating a lifting force. The principle works because of the conservation of energy. Total energy in a closed system remains constant. When air accelerates over the wing, its kinetic energy increases, which leads to a corresponding decrease in its potential energy in the form of air pressure. However, Bernoulli's principle doesn't explain everything about lift, and we can't solely rely on it to understand how wings work. Another key explanation comes from Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. In the case of an airplane wing, this law comes into play through the downward deflection of air. As the wing slices through the air, it pushes the air downward. In response, the air pushes back upward on the wing with an equal force, generating lift. This reaction is often referred to as the downwash effect. In reality, both Bernoulli's principle and Newton's third law work together to generate lift. The airfoil is designed not only to create a pressure difference, but also to deflect air downward. The combination of these effects produces the lift necessary to overcome the weight of the airplane and keep it in the sky. Another critical factor in generating lift is the angle of attack. The angle between the wing's chord line, an imaginary straight line from the leading to the trailing edge of the wing, and the direction of the oncoming air. By increasing the angle of attack, the wing deflects more air downward, generating more lift. This is why, during takeoff, the pilot tilts the nose of the plane upward to increase the angle of attack and generate enough lift to become airborne. But there's a limit. If the angle of attack becomes too steep, the airflow over the wing becomes turbulent and breaks away from the surface, leading to a dramatic loss of lift. This phenomenon is known as stalling. In a stall, the plane no longer has enough lift to counteract its weight, and it can begin to descend rapidly unless the pilot reduces the angle of attack to restore smooth airflow over the wing. In addition to the shape of the airfoil and the angle of attack, aircraft use several mechanical devices to enhance lift, especially during takeoff and landing, when more lift is needed at slower speeds. These devices include flaps and slats. Flaps are hinged surfaces located on the trailing edge of the wing, and when extended, they increase the curvature of the wing, which increases lift. Slats, located on the leading edge of the wing, are used to direct air over the top of the wing at higher angles of attack, preventing the air from separating and stalling. These devices allow pilots to adjust the lift properties of the wing to match different phases of flight. For example, during takeoff, extending the flaps increases lift and allows the plane to become airborne at lower speeds. Similarly, during landing, flaps help to maintain lift as the plane decelerates for a controlled descent. In summary, the generation of lift by an airplane wing is a complex interaction of aerodynamic principles. The shape of the wing, the airflow over and under it, and the laws of physics all come together to create the upward force we call lift. Whether through Bernoulli's principle, Newton's third law, or the use of mechanical devices like flaps and slats, the science behind lift allows us to achieve the marvel of flight. So the next time you see a plane soaring through the sky, you'll know just a bit more about the invisible forces keeping it there. Thanks for watching, and if you found this video interesting, don't forget to like, share, and subscribe for more fascinating content on science and aviation. See you in the next video. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.